We raise your hands in case we have multiple people, or we can start with whoever we see, right? So let us start this session. So who wants to go first? Maybe you could raise your hand and then we'll pick and choose. If not, you can just unmute yourself and ask the questions. Yeah, go ahead, Kshitij.
Sir, I had a basic doubt. Like we were studying about the P measure and Q measure. So I
Yeah.
was just confused between the which is the natural probability measure and which is the risk neutral probability measure. And
Yes,
what do we mean when we say we are risk neutral, sir?
right. So the second part of the question, right, I'll answer later, in the sense that we'll be covering it in one of our later sessions. And let me come back to the first part of your question as to what is a risk neutral probability measure. So sorry, what is a natural probability measure? So natural probability means how it naturally evolves, right? What are the actual probabilities associated with the evolution of a particular stochastic process, right? So for example, if I ask you, you know, generally we consider coins as fair, right? So if you take a coin and if you toss it, right, so you'll get heads and tails and you'll consider this to be fair, right? But this may not be the case, right? So for example, if you take a coin, right, and you actually do heads and tails many times, you know, maybe 1,000 times, 10,000 times and all, okay, and if you find that the probability of heads is zero point 0.6, right, and tails is 0.4, then since this probability we are getting by performing experiments on that actual coin, right, we will call this as the natural probability measure of that coin. Okay, so these probabilities which are associated, these are natural to that coin, or actually how the coin evolves over a period of time, right? What are the actual probabilities? So that is what we mean by natural probability measure. So for any stochastic, so not related to only stocks, related to any stochastic process. Stochastic means anything which is uncertain and which is measurable, which has a measurable outcome, right? Measurable outcome means you know what all the outcomes are going to be before the experiment is going to be performed. For all such probability experiments, when you perform experiments and you find what is the probability associated with each of its outcome, then we call that as the natural probability measure. Okay.
Okay, sir.
So that is what is natural probability measure. Point is that's not only one. You can associate more than one probability measures with the same process. Why are we associating a different probability measure with the same process? Why are we going to risk neutral and all? We'll discuss that as part of our third week sessions, where we'll discuss about Black-Scholes derivation and all of that. So we'll keep that part reserved for week 3. But point is, we have a stochastic process. Most of the times, whatever you have learned so far are all natural probability measure. No one calls it natural probability measure, but whatever you have learned so far is a natural probability measure. But when you associate something else and then you convert from one to second and use the second one, that's what we'll see later. So
Sir, I had another doubt, sir.
yeah, go ahead.
Sir, for the stochastic process, when we were deriving that the expectation will be zero only like for a unique value of P. Uh,
Yeah,
so the statement that we had written is like something like there exists a unique P for all L and M such that expectation is zero. And this was
right.
the condition for which we said that there was no arbitrage condition. And sir,
Yes,
at the another time when we were discussing martingale property, we
yes,
defined that there exists a unique P such that
yes,
for which a stochastic process is martingale. So is the two statements
right.
same, sir? Because I feel uh, like martingale is a kind of another definition, like for which some
Yes.
extra conditions need to be fulfilled.
No. So point was, the other day we were seeing a random walk. Okay.
Yes, sir. Yes, sir.
The random walk starts from 0. Okay. And then it has these probabilities associated. It starts from 0, it goes to +1, or it goes to -1, and with probabilities p, okay, and 1 minus p, right? And instead of +1 -1, that day I had written L and M, right? And here
Yes, sir.
that said was if you take the expectation, that has to be equal to 0, correct? So expectation will be P into L, right? Plus 1 minus P into M. This has to be equal to 0, correct? Now this exactly is the condition for martingale, right? For martingale, what I do is I do a little more generalization, and instead of calling it as 0, I call it as ST, right? So expectation, right, under probability measure P, right, which is P and 1 minus P of ST, right? It takes two values L and M, right? So this process should be equal to ST. ST is its value at time t is equal to 0 or here, correct? This is t is equal to 1, right? So this is called as a martingale, right? And in specific to our this example, this was equal to 0, right? That is why I said that if you set it to 0 and then solve, then whatever you get as a p corresponding to respective L and M's is that probability measure for which it is 0. The actual condition is not of being 0. Okay, that was a specific example. The generic case is that it should be equal to ST.
Okay, so got it, sir.
Okay.
Yes, sir.
Yeah. Any other questions?
Sir, sir, in third question, sir, I have only printed. So while solving the third question of assignment 1, what I do that I take a sample test case of random number, then I find the respective p of xy or p of y n plus 1, and we print that. Is that answer is okay?
Can you repeat the question again?
So in the third question, sir, we have to prove p of x comma n plus 1 is equal to
Yeah,
summation of product.
right.
So sir, in this I take sir, some random array of
Yes.
value y comma n
Okay.
and y p comma x condition y,
Okay.
and I write the algo to calculate the p of x comma n plus 1.
Correct.
So I
So
print.
what you have to do is you have to uh, by performing experiment, right? You have to get the left hand side of the equation separately, correct? So I think which is p of x at n plus 1, correct? You have to generate this using performing your experiment. Okay.
Yes, sir.
Then you have the transition probabilities, right? Depending on whatever symmetric or asymmetric random walk you pick. Let us say you pick symmetric random walk, right? Then this will be 1 by 2, right? Into p of y given n, y1 given n plus 1 by 2 into y2 given n, right? So these also you can generate y simulation. You can check whether this is half. And even if you don't do it, it's okay. But at least these things you have to get generate y simulations, okay? And then multiply by these respective numbers and check that whether you get this or not.
Yes, sir.
Okay. But you have to write code in such a way that later if I want, I can change these values, right? I can make this 1 by 3 and 2 by 3, and I can check that this is true for generic case, right? And I can iterate over. So instead of y1 and y2, right? Then I can go to a different point and different places. And for example, z1 and z2, right? I can take z1 and z2 at this and then go to n plus 1. And instead of y, I can take q, right? And I can verify this, okay, again and again. So write the code in a generic format. Okay, but we are just checking it for one step, just to be clear. Okay, I hope this answers the question.
Yes, sir.
Okay. Now, any other question by anyone?
Hello, sir, can you hear me?
Yes, I can hear you, Archit. Go ahead.
Sir, could you please explain the stochastic process?
Sure. And let me explain with an example. Okay. So let us say that there is a student, right, who takes an examination, right? Let us say he appears for an examination of a subject, let us say maths, right? Let us say a student appears for an examination, okay, of maths, right? Then what happens? Okay, let x be a random variable of the number of marks he scores. Correct. Let us say always the exam is out of 100. So his score, right, ranges from 0 to 100, right? He cannot get any other score. So he'll get anything between this and he'll get only integers. Okay. So in the first exam, the student gets 28. In second exam, he gets 42. In third exam, he gets 64, right? So the collection, so stochastic process XT is defined as collection of all his scores in different examinations. Okay. So X1, X2, X3, so on up to Xn. Okay. So all collection of the realizations of the stochastic process. Realizations are generally denoted by small letters. So I'll just update it. Okay. So this is X1, this is X2, this is X3. Okay. So collection of all these is called a stochastic process because this evolves over a period of time, right? So it might have a certain property. For example, between each of the examination, if the student is preparing, right? So he's studying again and again, and assume that the syllabus is same between the examinations, then what you should expect is over a period of time, his score is expected to improve, correct? So this is a certain behavior of this stochastic process, correct? Correspondingly, every stochastic process, for example, a random walk has a behavior, right? So if you keep tossing coins which give +1 and -1, over a period of time, there is some behavior expected, right? That it keeps going up, down, something, and so on, depending on the probabilities.
Yes, sir.
So that is why this is the motivation to have a stochastic process, how it evolves over a period of time.
Okay, sir. So where does the Brownian motion come into picture?
So when you take a random walk, right? So random walk is, let me hide this. And just give me a second. So when you have a random walk, right? And if you keep, so if you have a random walk, right? So this gives +1, this gives -1 with probability 1/2, right? And you keep evolving this over a period of time, right? So there is a certain behavior which you see. So 1/2, 1/2, you are here, 1/2, 1/2, branchings, right? And so on and so forth, right? So this is between time 0 and capital T, right? Now, and your each time step, right? So this is T1, then you have T2, right? So your each time step, within each of your time step, your stochastic process is evolving, right? So if I take actual plot of stochastic process, right? So at time between 0 to T1, right? Let us say it went one up, right? So it went one up like this. Then from here it went to 2, then it went to 1, then 0, then something like this, right? So if you plot all of this, right, this pretty much looks very similar to what you see in your as a stock price, correct? So if you take any graph of a stock price, so images, right? So this is what you see, correct? So we are trying to simulate this observation of stochastic process by using a certain mathematical framework. The framework for that what we have chosen is a random walk. And when you take a limiting case, right, when you keep reducing these delta t's, when you keep making this smaller and smaller, right? So difference between these two. So take this as, let us say capital T is 1 year. Okay. So let us say you have 1 year graph which looks like this. Okay. Now I keep dividing it into smaller and smaller intervals, right? I take T1 is equal to, first I take T1 as 1 day, right? So T2 as 2 day and so on. Then I take this as, 1 minute, this as 2 minute. When I take this as 1 second, right, 2 seconds. As I keep making it smaller and smaller, it very closely resembles what is a Brownian motion, what is called as a Brownian motion. Okay, I mean it
Okay,
follows
sir.
geometric Brownian motion, but we'll come back to geometric Brownian motion and all little later. But for now, for sake of simplicity, just assume that it is Brownian motion. It actually is not Brownian motion, it is geometric Brownian motion, but we'll come to that later. Okay, we are yet to build on that. But the
Okay.
final objective which we are trying to do is, let us say in one realization, this is how the stock price has evolved, correct? So if I restart the experiment from the same time and re-perform this experiment again and again, 100 times, 1000 times, 10,000 times, then how will my stock process evolve until my end of time? Okay, that is what we want to simulate. Okay, which is for which we are trying to build a basic mathematical framework.
Okay. So, sir, does every
Yeah, go ahead.
sir, can you hear me?
Yes, yes, I can hear.
Yeah. So, sir, does every stochastic process follows a Brownian motion always?
No, no, no.
No.
There is a very special property of stock prices which gives us the flexibility, or which makes us to use Brownian motion. But there are two things. Okay, so for example, your underlying stochastic process, right, might have any distribution. Okay, but the average of those random variables, right, x bar, that follows a normal distribution. Okay, which is one of our exercises of central limit theorem and all of that. Okay, and because of which what happens is, if you actually take stock prices, okay, take historical data of stock prices, okay, and then you take the log returns, okay, log returns of stock. Okay, the log returns are defined as, you take log of stock price at time, let us say t equal to, let us say 5 days, divided by stock price at 1 day, something like this. Okay, or you can take log of stock price at day 2 divided by day 1, right? You take this log. Okay, and whatever values you get, okay, you plot the frequency distribution of it. Okay, that will very closely resemble a normal distribution, and because it resembles a normal distribution, we are going to take Brownian motion for it. Okay,
Okay,
but
sir.
there are
Got
other
it.
stochastic processes. For example, there is called as Poisson process. Okay, and there are other stochastic process. For example, Poisson process is used for bond pricing and for credit derivatives. Okay, there Poisson is used very frequently. Okay, but
Yes,
most
sir.
of
I'm aware.
but most of the derivatives which we have, for example, interest rate derivatives, then you might have FX derivatives, then commodity, then you can have stocks, right? For most of them, you can use a Wiener process, which is normally distributed.
Okay.
Yeah.
Okay, so that clears it. So one more doubt. I was looking forward to the filtration process. I
Yeah.
understood the process, but I didn't understand the meaning of it. Like, why do we use it? Like, what does it actually mean?
So every other definition, right? Every definition. For example, when I say that a stochastic process is a Markov process, right? The way I define it is probability of something happening at time n+1. Okay. The way I write it directly, I write it as filtration ft. Okay, is equal to probability of something happening
Yeah.
at n+1 given xn. Okay, so this filtration helps me save a lot of things. Okay, otherwise how I've tried this definition is probability of xn+1, okay, given x0, x1, x2, so on up to xn is equal to probability of xn+1 given xn. Okay, so I don't need to write this. I can simply say that this is as per filtration. Okay, by filtration means whatever has happened so far. That is the meaning of filtration. Whatever information is available to you, according to that. Okay, so that spares me this thing. What will happen is if you read a lot of white papers and all, right, they'll simply define martingale as expectation of stock price given filtration is equal to stock price, right? So you get confused as to what is this symbol and what it means. Okay, that is why I took the first session about what is a filtration and what is a probability measure. Now understand that filtration is same for every stochastic process. Okay, once you have defined the stochastic process, filtration will be same. Now mapping of filtration to probability measure to 0 and 1, okay, is called probability measure of a
Yes,
stochastic
sir.
process. Now you can have different probability measures associated with the same stochastic process with the same filtration. So same filtration can have 0 to 1 with a natural probability measure and 0 to 1 as per risk neutral probability measure or Q, right? For that, it is important to understand that there is something underlying filtration which is mapping to 0 and 1, but in a different way, not as the same way. So this is what
Yes,
using a filter.
got it, sir. Thank you.
Okay, welcome. I hope people have got an opportunity to at least take a stab at the assignment questions, right? At least once you have solved them, so that you have all your questions related to assignments also, right, along with the content which we have covered. So you ask all of those questions. I assure you, any assignment does not require coding beyond 6 to 8 lines. Okay, so it's not very detailed elaborate coding yet so far. We'll do some coding later which might require some big codes, but no coding is beyond 5 to 6 lines of codes. Even though we are starting from first principles and not using any custom Python libraries. If you use custom Python libraries of random walk and all, less than even 2 to 3 lines. Okay. Any other questions by anyone? Regarding second assignment, regarding partial derivatives, regarding, of course, see, everything we have studied will always are going to build on it. Okay, so nothing is taught for the sake of teaching. You will see application of every single thing what we have learned in the coming sessions. Any other questions? Question on quadratic variation, Wiener process. If no other question, I'll just go over one concept again, right? I think a lot of you have the same doubt, right, which comes up again and again, right? Why we have I mean, why martingale? Why martingale means zero probability? I mean, no arbitrage and all of that. Okay, I'll try to explain that concept again. No arbitrage, martingales, and all of that, but with a different set of examples. Okay. So first, let me take a non-probabilistic example. Okay, and let me explain what arbitrage means. Okay, so let us say there is a guy. Okay, so there is a person who is selling. Okay, he's selling idli. Okay, and vada. Okay, so that's the story he has, and these are the two products he has. Okay, now this guy sells one idli for 2 rupees, and he sells one vada for 5 rupees. Okay, and he also sells a combo. Okay, and he sells a combo of 2 idlis. Okay, and 3 vada. Okay, for 13 rupees. Okay, and this shop is special, right? At this shop you can both buy and sell. Okay, so it's not only as if you can go and buy from this guy, but you can both buy and sell to this guy. Okay, at the same quoted rates. Okay, so is there any arbitrage here? Okay, arbitrage means riskless profit. Okay.
Yeah, we
So
can
without
buy it from the guy who's selling 2 idlis and sell it to him.
Okay, so you're going to buy from whom and sell to what?
Buy from whoever is giving me the lesser and sell it to whoever is
Yeah,
offering me the highest.
in this case, what will you do?
So you said the first guy is selling how many
No,
idlis?
no, it's the same guy. Okay, it's the same guy. Okay, he's offering me 3 products. He's selling me either one idli for 2 rupees. Okay, or he's selling me one vada for 5 rupees, or he's selling a combo to me of 2 idli and 3 vadas for 13 rupees.
Okay.
So how
Sir,
do
we'll
I
buy the
make?
combo and
So we'll
then
buy the combo.
Okay, so you bought the combo from him. Okay, then
And then sell 3 vadas at 5 rupees.
Sell.
so 3 vadas will give you 15, correct?
And two idlis will give 4 rupees.
2 idlis into 2 will give you 4 rupees, right? So total this is 19 rupees. So profit is 6 rupees, correct?
Yeah.
Now, for how many price points, okay, do these idli vada prices and this combo prices agree? You get my question? What is the combination? I mean, for how many combinations, right? Can you I mean, assuming one of it is constant. Okay. So there are three elements, two of which you will have to keep constant and something like that. Okay. For how many combinations can you have the prices, right? So the point I'm trying to make is there is only one combination which makes it arbitrage free. Right? For any other combination which he uses, there will always be a profit. Correct? For example, he'll have to necessarily sell this combo at 19 rupees only. Correct? For any other combination he uses, there will always be an arbitrage. Okay.
Yep.
So now let us
Yes.
think through this. Okay. Now let us think through this. Okay. He keeps it 13. Okay. So just now what all of you said was you will buy this combo. Correct? You will buy this combo and you will sell out these things. Correct? So what is happening is you're buying this combo from the same idli guy, right? And you're selling it back to him only, correct? Because he can both buy and sell. Okay. So what will happen is over a period of time, since you're buying this again and again, correct? And you're selling back to him, right? Then this price will rise, correct? Because there is a demand for this, and this will fall because he has a lot of supply of this. Okay, correct? So,
Yeah.
so these prices will adjust such that this ends up at 19. Okay, because if you start selling this at 20, you will start reversing the transaction, correct? You will
Yep.
start buying individual components from him and start selling back the combo to him, correct? So there is only one price point at which all these things agree with each other.
19.
Okay, and there is no other price point at which it agrees, right? So that is why, so that is the point that I was trying to make the other day. Okay, so you have a stock, right? And you know that stock is priced at 100. Okay, and the stock has possibility to go to either 105, okay, or 103. Okay, now you have to remember that at this point in time, okay, to make money out of it, at time t is equal to 0, what do you have to do? You have to first buy this stock, right? You don't own it, correct? You have to first buy it.
Correct.
Okay, and here at this point at time t equal to 1, you're selling it, correct? So this automatically becomes your cost. Okay, at this time what happens to your cash flow is minus 100, right? And when you're selling it back, it either becomes plus 105 or plus 103, correct?
Yes.
So this part is already the cost of playing a probability game, correct? And this is the reward of playing that probability game, correct? For example, if I ask you, there is a guy, right, who gives you, he's tossing a coin, okay? And if head comes up, he gives you 4 rupees, and if tail comes up, the same guy gives you 2 rupees. Okay, that guy has to charge you something to play this game, correct? Am I right or wrong? Right? If that guy does not charge you anything, so if he charges 0 rupees, right, then what, then how can you make money out of this? You will place, okay, one bet on this and one bet on this, right? That either this will occur, or so 1 rupee on this and 1 rupee on this, and you can keep making money out of it, right? You'll place bet on both things, correct? That is why, so the only way there will be no arbitrage is that you will, the whatever is your cost of purchase of that asset, okay, and present value of your outcomes weighted by probabilities, you know, expectation of your outcomes, when both of them match, right, only then there is no arbitrage. I hope it makes sense.
Yes.
Yes, sir.
Right? Only then there is no arbitrage if this matches, okay? And this thing mathematically is written as martingale. So expectation of st, okay, is equal to, now under this probability measure, okay, is equal to today's price itself, okay, because this is cost of playing the game. Okay, and this is your reward, what you get out of playing the game. Okay, now the interesting part is you don't need to know your actual probabilities or your odds of winning the game. Okay, unlike this game coin toss. Okay, here there is a very clever argument because there is something which you can do with this stock what you cannot do with this coin toss. Okay, and that is called as setting up a riskless portfolio. That you can do with this using derivatives that you cannot do with this coin toss. That is why in coin toss, only if you know this probability of coin going up and down, okay, only then you can set what should be the price of this playing this game. I hope you get what I'm saying. Okay, if you don't know these natural probabilities in a coin toss, even as a person, okay, who is going to make money by making people play this game with you, you will not be able to set the correct price of it. If you keep too less price, then people will make money. If you keep too much price, no one will come to play with you. Okay, so because like I said, there is something which you can do with this using derivatives market, which you cannot do here, which we are going to study in our later sessions. Okay, so here what we are putting condition is I don't even know what the natural probabilities of getting 105, 103 are. But if under any probability measure, let us call it Q, okay, it can be any other probability measure. Okay, I am myself, okay, I am whatever I think are the correct probabilities. Okay, I am assigning some probabilities P and P star and Q star, P and 1 minus P star. If there exist such probabilities such that expectation of this under that is equal to this, then also I'm okay with it. I don't need to know what are my actual probabilities. That is the beauty of it. Okay, so this happens because derivatives markets exist. So it is a precursor that derivative market should exist so that you can use other set of probabilities and not the original probabilities, and still you will work fine and you'll be able to find the expectation and all. Okay, so I hope this makes the point, right?
Yes, sir.
Yeah.
So this is what a martingale theory is, sir?
Yes, this is martingale.
So basically not having an arbitrage as the end goal.
Yes.
Okay.
Now you're correctly hitting the nail on the head. Okay, our objective is not to find where the stock price is going to go. Our objective is to find under what probabilities that underlying is going to be riskless, or we'll come to that riskless point later. But under what probabilities the cost of playing that game is equal to be the expected reward of playing that game, so that net you are not going to win out of that game or lose out of that game either.
So that's what called riskless,
Yes.
where you don't win or either lose. It's neutral.
Yes, because it is called riskless because you know what is going to happen with you going ahead. Correct? There is no uncertainty with your future on an average. So if you play infinite number of times, you know you're going to where you're going to end up. That is why it is riskless. Any amount of reward is going to be associated with risk. There cannot be any reward without any risk. So you are making your reward zero on an average. Okay, and then saying that is why you are riskless.
But are there any in the real world? Are there any riskless assets, but still there is a reward? Like what kind of instruments?
That is called as arbitrage. And you can have arbitrage. On the contrary, because people believe that their arbitrage is possible, hedge funds exist. If it was impossible, there is no objective for hedge funds to exist. Okay, then because of which, in a certain sense, right? In a certain sense, that because under probability P measure, there exists a probability P measure which is not equal to Q, and so on and so things. Because which is why your mutual funds exist. Okay. So let me show you what is expectation of a stock price under a natural probability measure. Okay, so expected stock returns.
So you are saying like there is no risk to get a reward, right? So if there are like multiple events where
Okay.
somebody is taking the least amount of risk and somebody is taking the highest amount of risk.
Okay.
So of course, somebody who's taking highest amount of risk is going to win big, right? So how do we know like?
No. You committed one small mistake there. Okay. You assume that high risk means high returns. Okay. All I said was high returns require high risk. Both are
Yes.
not. What can I say? Both are not equivalent statements.
So you are saying high returns comes with high risk.
High returns require high risk.
Right.
Without
Correct.
high risk, you cannot have high returns. But I never said that, you're taking high risk, that means you're going to get high returns. Because that
Right.
depends on quality of risk. There is a good risk, there is a bad risk, there is a diversifiable risk, and all of that. Okay.
So how do I know like how much to get the maximum reward, how much risk to take?
Which is what it comes from this model, right? CAPM model. Okay, which is what I was kind of showing to you. But the point that I was trying to make was here the expectation which you take of stock returns, okay, is under natural probability measure. Okay, so here that guy is saying that your average returns are going to be risk-free returns plus something. Okay, but under martingale, your average expected returns are going to be risk-free returns. Okay. So all I'm trying to say is there are two probability measures. Both probability measures have different expected returns, and both of them are correct in their own places. Okay. Expectation of returns under Q probability measure is equal to risk free. That is also correct as far as derivatives is concerned, because it has a risk portfolio can be set up. Whereas this guy saying that expected returns is equal to risk free plus something else, which is also correct, because this is under natural probability measure. This is something else, that is something else. Both of them start from quant finance and or build on top of that. So we'll come to see this. We'll see this in 4th week and all of that. Okay, we'll study this in detail. But this is other part of the quant world. I hope I have managed to confuse you thoroughly. Yeah, any other questions?
I mean, this one is little clear, sir, but I'm actually confused between the stochastic process and the Brownian motion.
Okay, so is there any specific question so that I can address it? If you want, I can simulate and show a Brownian motion to you.
Yeah, please, sir.
What are
So
properties?
all Brownian motions are a part of stochastic, but not all stochastic processes are Brownian motions.
Correct. A very specific case where the increments are normally distributed is Brownian. You can have non-Brownian. You can have Poisson, like I said, right? Brownian is I don't know because it was discovered by Robert Brown. But if you want to name stochastic process by distributions, I will call this as normal process, correct? Normal distributed process. Then you have Poisson distributed process. Like I said, you can use n number of distributions. You have Levy distributions and all other. Okay, so you can have other things. So how does our Brownian motion look like, right? So what are the properties of Brownian motion? It starts with 0. Then increment, right? So this is time t equal to 0, and this is time t equal to 1. This is 2, this is 3, so on, right? So between 0 to 1, okay, it is normally distributed. So the random variable is normally distributed. That is why I have to generate a random number, right, which is normally distributed. Okay, and between 1 to 2, it is also again normally distributed with mean 0 and variance 1, correct? Here it is again normal distributed with so mean 0 and variance 1. That's why I chose norm inverse of standard distribution and used a random number to generate that random number. Okay, so this is how it is evolving, right? So this is W1 minus W0 W0. Okay, then this part is W2 minus W1. Okay, and this part is W3 minus W2. Now every random number which is getting generated here, okay, is not connected to the random number which is generated here, right? That is why the increments are independent of each other. Then they are continuous. Then they start from, so the winner process starts from 0, and the fourth property is that it is normally distributed with mean 0 and variance 1. All properties are satisfied. Now if I add these two, okay, what I get is W2 minus W0, correct? If I add these three, what do I get? W3 minus W0. So to generate a random, so to generate a Wiener process or Brownian motion, all I have to do is go here, then go here. So I have generated Brownian motions for n number of trials. All of them start from 0. Okay. Now this is this plus this, and this is what happened previous, what happened between the two. And I keep simulating it. Okay, and I keep dragging it. Okay, so these are our Brownian motions, all of which start from 0. Okay, so these are all our Wiener processes. If you do enough number of simulation and you take cross section at any point in time, right, you will see that it is normally distributed with mean 0 and variance capital T.
So does this resemble a random walk?
Yes. So that's what we have an assignment for, right? We have a central limit theorem. So if you kind of prove that, then you kind of prove this. Okay. What happens is Actually, so if and plus if you have a random walk, okay, let me show random walk movement. It should not take long. It starts from 0 also. Okay, in each iteration it will generate a random number, and then if that random number is greater than 0.5, we call it 1, else call it -1. This, then what you're going to do is this is going to be this plus this, and this is going to be this plus this. So cumulatively it adds up. So go this and then go this, right? And then you have zeros, and then see how it looks like. Okay, this is not proof, this is just intuition. Okay, now as you keep reducing these time lesser and lesser, right? This is between 0 and 1. Okay, now between 0 to 1 you can divide it into 10 parts, and for each of those 10 parts you can have again generate these numbers between 0 to 1, correct? And when you plot it, so limiting case of this, as this delta t tends to 0, is this. Okay, and simply if you square all of these, right? So if you square w1 minus w0 square plus w2 minus w1 square plus w3 minus w2 square and add it up, it should add up to your t. So t is whatever is your time, right? So if you do it up to 10, so it should add up to 10. That is our quadratic variation, which we just saw. Now instead of starting from 0, start it from here. Okay, so instead of starting from 0, if you start it from 10, okay, then what you end up with is your gambler's win problem, right? So it's still coming down, but if you increase the number of trials and all, it should match up perfectly fine. Okay, for some parts it will reach 100 and some not. Okay, any other questions? So we can continue with our questions on our chat as well, right? So in case you have some more questions, you can ask on chat, because someone else might also have similar questions. So do ask on group so that we can clear it up there. Okay, and all the best with your assignments. Okay,
Thank you, sir.
sure, happy to help. I think we can pretty much close this call. Thanks everyone for joining. Bye.